So let's take a look at the setting we have so far. How did we attempt this problem? Right. A listener can be forgiven for feeling that this is oppressive, this was difficult, there are lots of moving parts and it was not clear where they came from, and at the end something magical seemed to have happened. But let's take a look at it piece by piece and deconstruct what we have done. We were interested in the chance of a success run occurring somewhere in a sequence of n tosses. The first and natural step was to seek a partitioning to break it up into smaller pieces, and the natural partition was to break it up in terms of the first success run events. Okay, so maybe that wasn't too bad, though assuredly if someone without a background in this, without preparation, had been thrown to the wolves, as it were given this problem, it might have been hard to unearth that particular way of breaking up the problem. But you will agree with me that at any rate, once pointed out, it is clear that this is an elementary and perhaps even natural, maybe even inevitable way of breaking up the problem. Well, that was our first equation. The second equation was a little more complex. We now had an issue of trying to compute the probabilities Fn, and we related it to the probabilities Un, the probabilities of the first or subsequent success runs terminating at trial n. And it's not clear where this line of thought came from. If we deconstruct and look at what we have done, having the advantage of having done it, it is clear that what we were trying to do was understand success runs terminating at a certain point. And once we started thinking along those lines, we found we could break things up naturally based upon where the first success run terminated. And that led to an additive principle. And that additive principle led to a convolution, that expression in the middle. Okay. Now, so far so good. In itself, it is not daunting. Once you explain the principle, you say, oh yeah, I get it, I can see how this works. But again, extracting that principle from first principles without advanced training could be very difficult. The train of logic can be very slippery. But what I would like to communicate to you is that even though the initial step might have been hard to find, once it was pointed out, the execution was elementary. It just required additivity. Now, these two steps, as I told you, are generic. Nothing in these steps really demanded that we were tossing a coin. We could be doing any other experiment which involved repeated independent trials of the experiment with some events which constituted renewals. And if we had any such setting, then the first two equations will carry through in toto, without change. Where does the particular flavor of the coin-tossing experiment come into play? Aha, it is in the third equation. And it is here that we utilized what we knew about coin-tossing. What was the logic behind this? In many ways, this was the most slippery of the three pieces. The principle was very hard to find, because there are so many things which we could have thought of doing, which lead us into dead ends. And what unlocks the logical door here was an appreciation that we are dealing with a run of 5 successes. And if we looked at a particular run of 5 successes, from trials n through the preceding trial n-4 before it, then the understanding arose that you can't have such a run of successes without a success run terminating at one of those 5 locations. Admittedly, when I just say something like this looks like stony ground until that last observation hits me. And then I realize, that's an epiphany. I've got now a recursion. Admittedly, this is logically really difficult, and I would not be able to blame anybody if they'd been unable to unearth that particular logical strain which led to that equation. But the moment it is pointed out to you, then assembling that equation after that fact is not hard at all. It is additivity once more. beautiful, nuanced, subtle. Now, at the end of the day, I have three equations. All of them just require an elementary use of additivity. Never confuse the word elementary with easy. Elementary here just means you don't need any fancy tools, you don't need any big electronic widgets. You just need very basic principles. The difficulty here is not in the fact that the technical demands are very high, but that the logic is very slippery and it takes time, effort, and maybe a touch of genius to extract the right approach. But once you have the right approach, executing it requires nothing fancy whatsoever. It is simply just the whole is equal to the sum of the parts repeatedly. Now, this long peroration is perhaps useful for a reader, for a listener, to not feel oppressed by the fact that this was so hard. The pieces were hard to discover, but once we understand what the key logic was, then it is easy to assemble. Having put this much work in, we should see if we can extract a little more juice from this apparently stony stone. Right. How could we extend this idea? Well, we could go in two directions. We looked at success runs of length 5. Naturally enough, we would like to say something about arbitrary success runs, say success runs of length r, where r could be 1, 2, 3, 4, 5, and so on. Well, what changes here? Well, the first two lines remain intact. They carry through in toto. Nowhere in the logic in those first two equations did we exploit the fact that the coin was fair, or that we were dealing with coins at all, actually. The fairness of the coin arises in the third equation, and it arises in the powers of 2. 2 to the power minus 5, 1 half times 1 half times 1 half times 1 half times 1 half. 5 successive successes in coin tosses. 2 to the minus 4, 2 to the minus 3, 2 to the minus 2, 2 to the minus 1. Here's where the fair coin was used, and here's where the number of successes was relevant. 2 to the power minus 5, we were dealing with 5 successes, success runs of length 5. Well, what happens if we replace success runs of length 5 by success runs of length r for some generic positive integer r? Everything carries through in toto. With the replacement of 2 to the power minus 5 by 2 to the power minus r, and now we're going to look at a block of r successes running from n through the r minus 1 trials before it, and then break it down exactly the same way. But now we have a new equation with 5 replaced by r. Oh, that was easy. What if the coin were not fair? Well, where does the fairness of the coin come in? Well, it comes in the powers of 2. So, but instead of 1 half, if you had a biased or a bent coin whose success probability is p, for some p, then 1 half gets replaced by p. 2 to the power minus 1 gets replaced by p. 2 to the power minus 2 gets replaced by p squared. 2 to the power minus 3 by p cubed, and so on. And now we've got a new equation. Everything carries through in toto from this point on. And so from here, you can compute for a given p and a given r all the values u. From the u values, you can compute all the values f. From the f values, you can compute all the values s. And notice we've got a general overarching principle, and now a principle which has got more utility than the simple, controlled, limited problem that we started with.